In this lecture, I want to basically go through the same transfer function that I went through on the Bode plot looking at the magnitude plot, except this time I want to emphasize the phase plot. So we'll take the same function that we previously had. Basically, Bode plots are used to display, as we said before, the phase and magnitude of the frequency response of a transfer function h of s. And there are several steps that are involved in creating a Bode plot. So the first thing we do is we replace s with j omega. Now, to construct the phase plot, what we then do is we find the phase of each factor of h. At that point, remember the phase angles add when they're in the numerator and they subtract when in the denominator. So we can combine all of those to basically be a sum of different phase angles and getting rid of the fraction. We then plot the contribution of each term in the phase as an asymptote, and we fill in the curves between the asymptotes. And once again, you recall that Bode plots are quite easy to do in MATLAB. So here's the example that we used before. So a couple of things. First of all, you'll notice that this function does have a gain that is not equal to 1. We would actually find the gain by looking at this factor in the numerator, which is 10, and then in these denominator terms, letting s approach 0, which would mean j omega was approaching 0, we would get 10 times 1,000. So on the very, very low frequency end, you can see that this is actually a band pass filter. So the gain is a little more difficult to compute, but basically we would have a gain that was not equal to 1. In the magnitude plot, that makes a difference. A gain different from 1 shifts the Bode plot vertically up or down depending on whether the gain is greater than or less than 1. In the phase plot, it doesn't matter because basically a gain is a magnitude only curve. It has a phase angle of 0. So the phase plot will not be shifted up or down if there is a gain that is not equal to 1. So we're then only going to consider the term s and then the term s plus 10 and s plus 1,000 in the denominator. So like in the previous example, the first thing we do is we substitute j omega for s, and then simplifying as you wish. In this particular case, you actually don't have to do this simplification step on this third line. You can actually stop right here because remember we're going to be trying to find the phase. Now, how would we find the phase of a complex number that looks like this? The easiest way to find the phase is to do it term by term. So in the numerator, we have 10 times j omega. Notice that this is only an imaginary term, and so we already know that the numerator term has a phase angle of 90 degrees. The denominator, this first factor, j omega plus 10, we'd find the phase angle by taking the inverse tangent of the imaginary part over the real part, so the inverse tangent of omega over 10. And then here, same thing, we'd find the phase angle by taking the inverse tangent of omega over 1,000. All right, so I'm sorry, I actually have a typo here when I was doing my copying and pasting. Sorry, when I was doing my copying and pasting and finding the phase angle, you notice I put the j here. You actually you would have that for the first term, but typically you would just have imaginary over real. So if we look at this first term, we already knew that that had a phase angle of 90 degrees because effectively it's imaginary part over 0. And so that's always going to be infinity because there is no real part in the numerator. So that numerator phase angle is 90 degrees. If we look at this term, and please ignore my error here where I have the j. Well, actually, let's go and look term by term. So the inverse tangent of j omega, and actually that should be imaginary over real, and the real is 0. So this is going to go, since there's only an imaginary part, this is basically going to go to infinity. So we have 90 degrees is where we start with our phase. If we then look at this term, and once again, just ignore my j for now, notice that when omega is very small, then this number approaches 0. And so we have the inverse tangent of 0, meaning it has a phase angle of 0. But notice when omega gets much greater than 10, we begin to approach a large number. We begin to approach infinity. And so as we approach infinity, we would have the inverse tangent of infinity as omega gets much larger than 10. When omega gets much larger than 10, we basically have a phase angle here of 90 degrees. And since this was in the denominator, it's actually, when it comes up to the numerator, going to be negative 90 degrees. So from term 1, we started at low frequencies with a phase angle of 90 degrees. We subtracted 90 degrees because of that first term in the denominator, which puts us at 0 degrees, and that break point, or that asymptote, is going to occur at a value of 10. The third term is going to do the same thing, except it has its breakpoint at 1,000. You can see that if omega is much, much less than 1,000, this is basically the inverse tangent of a number close to 0, so it won't contribute to the phase. If omega is much greater than 1,000, then basically we begin to approach infinity, which means we begin to approach negative 90 degrees. So for this function, we basically would expect to see our phase angle begin at positive 90. At the first breakpoint, which would be 10 radians per second, it would transition to 0. And then at the next breakpoint, which would be 1,000 radians per second, it would transition down to minus 90. So we can make some generalizations just like we did with the magnitude plot. So when we have a transfer function, we have terms in s to the n. So this would be a polar or 0 at s equals 0, and n can be positive or negative. So substituting for j omega, this would mean we would have a term in our transfer function that would look like j omega to the n. Basically, the phase angle there will be n times 90 degrees. And like the magnitude plot, whenever we have an s to the n term, this dominates the low frequency behavior. The difference from the magnitude plot is that this is a straight horizontal line. So there's nothing analogous to a 20 dB per decade or a minus 20 dB per decade slope. It's just a constant horizontal line. If there is no term in that is just like s to the n, so say you didn't have an s in the numerator of this function we're looking at, then basically n is equal to 0, and so your initial phase angle at low frequency is just going to start at 0 degrees. Only when you have a term in s to the n in your transfer function do you start off at low frequencies with a phase angle other than 0. So once again, terms like this will dominate the low frequency behavior of the system. And just like in the magnitude plot, finding the low frequency behavior of the system is extremely important, because if you get the initial frequency, or if you get the initial phase angle incorrect, then everything you add to or subtract will be off by that amount. All right, so here's the same Bode plot that we used when we illustrated terms like s to the n. In this case, this was the magnitude plot, and we were looking at 20 dB per decade, 40 dB per decade, 60 dB per decade, and so on. Here's the phase plot. And so the phase plot just illustrates, if we just had a transfer function that was equal to s, our phase plot would just be a constant line here at 90 degrees. If it was s squared, it would be a constant line at 180. If it was s to the minus 1, it'd be a constant line at minus 90, and so on. So phase plots are horizontal lines. And then if we have transitions, there will just be a transition to another horizontal line. Okay, which brings us to the terms in s plus a to the n. So this would be like your poles or zeros located at a, and this would be nth order. So for the case of n equals 1, a phase of 90 degrees is added. If n is equal to minus 1, a phase of 90 degrees is subtracted. And you have an asymptote that occurs, or you have a transition that occurs at a. So the phase angle shifts asymptotically by n times 90 degrees. Okay, so if we look at how that would go, not for this function, but just for this term. So this is illustrating s plus a to the n, where a, I must have chosen to be, looks like I chose it to be 10 radians per second. Yes, 10 radians per second. So notice that this blue line is where n is equal to 1. So we go from a phase for this term, so this is s plus 10. We go from a phase of 0 and then we shift to a phase of 90 because n is equal to 1 for s plus 10. If it's s plus 10 squared, n is equal to 2, so our total phase shift will be 2 times 90 degrees or 180 degrees. So we start at 0, we end at 180. It's going to cross 90 degrees, or the center of those two, at 10. The lower lines are for n is equal to -1, -2, and -3 respectively, giving us phase shifts of -90, -180, and -270. So what you do is you find your pole, which in this case is 10 or 0. It's 10, so this is A, and you sort of mark this as a transition point. And then you figure out where you start and where you end, and that'll cross halfway at that transition point. So if you've got a total phase shift of -180 degrees at 10, so if it's 1 over s plus 10 squared, at 10 you will be halfway there, you'll be at -90. So that's how the phase plots for one specific term. Now it's additive, so if you have s over s plus 10, remember the s in the numerator starts us off at 90 degrees. And so this whole thing, if we had an s in the numerator, would shift up by 90. It would start at 90, and then the s plus 10 or s plus 10 squared in the denominator would shift you to your final value. Okay, so there are, as you know, some terms that don't factor into real roots. This is an example. In this case, the crossover or breakpoint will be at omega n. It's just that we don't have a perfect square in the denominator. So this behaves like a second order pole. The difference is the transition from the initial phase to the final phase is sharper. So this is the MATLAB code to generate that. So here we start at 180 because we had s squared in the numerator. We're going to end at 0 because we also have s squared in the denominator. So that has the effect of subtracting off 2 times 90 degrees in phase. So we start at 2 times 90, we subtract 2 times 90, meaning we should end at 0. Here is our breakpoint right here at 10, and you notice right at 10, we're halfway there. So this transition, I don't know if you can tell, it is a little bit sharper than the one where we had the perfect square. Here's an example as zeta, that factor, that damping factor, gets smaller and smaller. You see the transition gets sharper and sharper. As a general rule, filters, circuits, especially active circuits with op amps, don't love these sharp transitions. So the smaller zeta gets, notice in the magnitude plot we get this little hump here. It's starting to look like we have a resonance peak. And as that gets smaller and smaller and less like a perfect square, so your perfect square would be here at the bottom. It's a nice smooth transition where your cutoff frequency is at -3 dB off the gain. As you let that damping factor get smaller and smaller, you approach more of a cosinusoid or sinusoidal function. When you take the inverse transform, that's going to give you a bump here in your magnitude plot that's going to look a lot like resonance. So if you let zeta go to 0, this thing is going to go to infinity, and you're going to have an oscillator, not a filter. And this thing would be an instantaneous change. So basically, this is just looking, let's go back, remind you what zeta is. Zeta is this factor right here. So if zeta is 1, this denominator is a perfect square, s plus omega n quantity squared. If zeta is 0, this denominator is s squared plus omega n squared, which is a cosine function. So you can see how that works. So going back, looking one more time, as zeta gets small, that transition becomes more and more abrupt. This is just with the transition region expanded, like I did with the magnitude plot, so that you can see the abruptness. You also can see that no matter what zeta, is they all cross halfway. They meet at the same point, the 90-degree point at the transition frequency. All right, so overall rules for Bode plots, just to kind of sum things up, and I did this on the magnitude plot lecture as well. Terms in S to the n are going to determine the low frequency behavior. The magnitude plot is going to have a slope of 20 n dB per decade. The phase is n times 90 degrees. Terms in S plus a to the power n are going to change the slope by 20 dB per decade on the magnitude plot, starting at frequency A, and they'll change the phase asymptotically by n times 90 degrees. If they don't factor into real roots, so second order terms that don't factor into real roots, they factor into complex conjugate pairs, they'll act like S plus a to the plus or minus 2, except there will be a resonant peak in the magnitude plot at A and a sharper phase transition. So that's just a summary of what Bode plots look like and how to quickly get them from a transfer.